225 million kilometers from home, 7 months floating in a metal can. And when you finally touch the Martian soil, you realize that the system meant to produce your fuel back has failed. You have food for 18 months. The next return window? In 26 months. Do the math. It's not science fiction. It's pure physics. And the numbers don't lie. Why a mission to Mars could turn into a one-way trip. Welcome to a journey to the limits of human exploration. Today, you will discover why getting to Mars is already difficult, but coming back from there might be impossible. Let's get straight to the numbers that no one likes to highlight. The real risks, the challenges that engineering has not yet solved. Because before we send humans to the red planet, we need to face an uncomfortable truth. Let's start by understanding where we are. The distance between Earth and Mars is not fixed. Our planets orbit the Sun at different speeds, like runners on separate tracks. In the best orbital configuration, when the planets align, Mars is about 55 million kilometers away. At its worst, 401 million kilometers. That's why we can only launch missions to Mars every 26 months. A narrow window of time dictated by celestial mechanics. And even in the ideal window, with current technology, the one-way trip takes between 6 to 9 months. More than 200 days floating in the void. But the trip is just the beginning of the problem. Because once you're there, you need to survive and eventually return. And that's where the numbers start to get scary. You can't see. You can't feel it. But from the moment it leaves the protection of the Earth's magnetic field, it is being bombarded. Galactic cosmic radiation. Subatomic particles accelerated to speeds close to that of light by distant supernova. In 2013, the RAD instrument aboard NASA's Curiosity rover measured something disturbing. During the trip to Mars, 1.8 millisieverts per day. On the Martian surface, 0.64 to 0.67 millisieverts per day. Let's put this into perspective. Nuclear power plant workers on Earth have a safety limit of 50 millisieverts per year. An astronaut in transit to Mars exceeds that in less than a month. A complete mission, 180 days outbound, 500 days on Mars, 180 days return, exposes an astronaut to approximately 1.0 to 1.1 sieverts of total radiation. Studies show that each sievert of exposure increases the risk of fatal cancer by 5%. But it's not just cancer. Cosmic radiation damages DNA, affects the central nervous system, increases the risk of early cataracts, cardiac degeneration. On the International Space Station, still within the Earth's magnetic field, astronauts receive between 0.4 and 1.0 millisieverts per day, less than half of what they would face going to Mars. And on Mars, no magnetic field, without a dense atmosphere to block particles. You are exposed, constantly. So how do we protect astronauts from this invisible radiation? The short answer, we still don't know completely. Now imagine this. You have arrived on Mars, survived the radiation of the journey, landed safely, and then he realizes he needs a rocket to get back. A rocket big enough to escape Martian gravity and make the journey back. This rocket needs fuel, a lot of fuel, approximately 30 tons of propellant, a mixture of liquid methane and liquid oxygen. Transporting those 30 tons from Earth? Impossible. The rocket would be too heavy to take off from here. So what's the solution? Produce fuel on Mars. Use what is there. We call this ISRU, in situ resource utilization. The theory is elegant. Capture carbon dioxide from the Martian atmosphere, which is 95% CO2. React it with hydrogen brought from Earth through the Sabatier reaction. The result? Methane and water. Then, electrolyze the water to obtain oxygen. In 2021, NASA tested this on a small scale with the MOXIE experiment aboard the Perseverance rover. MOXIE produced 5.37 grams of oxygen in 1 hour, a historic milestone. But to fuel a return rocket, we need to produce about 30 tons of total propellant. MOXIE operates at 0.5% of the required scale. And here is the critical problem. No full-scale fuel production system has been tested in the Martian environment. None. Just theoretical models and laboratory experiments on Earth. Dust storms that last for months. temperatures that drop to 60 degrees at night, radiation that degrades electronics. If the ISRU system fails, a damaged sensor, a frozen component, a bug in the software, there is no plan B, out of fuel, no turning back, and it's no use for Houston to send replacement parts. Even at the speed of light, communications take between 4 and 24 minutes to arrive. Round trip? Up to 48 minutes of delay. There is no real-time troubleshooting. There is no rescue. And even if everything works perfectly, you can't just come back whenever you want. Do you remember the launch windows? Every 26 months, Earth and Mars align favorably. Outside this window, the amount of fuel required would be astronomical, or the trajectory would be so long that the resources would not be sufficient. So it works like this. You take off from Earth. You travel for 180 to 250 days, arrives on Mars, and then wait about 500 to 600 days on the Martian surface, almost 2 years, waiting for Earth and Mars to align again. Now imagine that something goes wrong. The ISRU system did not produce enough fuel, or a critical component of the ascent rocket failed, or a crew member fell seriously ill. You missed the return window. Next window? In 26 months, 2 more years on Mars, 2 more years of radiation, 2 more years of bone loss, 2 more years of critical resources being consumed. And their supplies were planned for a mission of 900 to 1100 days, not 1600 days, not 2000 days. Rationed food, water recycled to the limit, oxygen produced by systems that were never designed to operate for so long. And with each passing day, her body grows weaker. Because on Mars, gravity is working against you. Gravity on Mars, 0.38 g, only 38% of Earth's gravity. Seems like an advantage, right? Everything lighter, easier to move, but your body didn't evolve for that. In microgravity, like on the International Space Station, astronauts lose between 1% and 2% of bone density per month. The weight-bearing bones, spine, hip, femur are the most affected. On the ISS, astronauts exercise for 2 hours a day, using special equipment, elastic bands, artificial resistance. Even so, they cannot completely prevent bone loss. On Mars, the gravity of 0.38 g is not enough to keep bones healthy. Studies suggest that the loss would continue, perhaps more slowly than in total microgravity, but it would continue. 500 days on Mars. You can lose 10% to 15% of bone density in critical bones. This is called osteopenia. Keep it up, and it will turn into osteoporosis. Fragile bones, very high risk of fractures. And here's the problem. To return to Earth, you need to survive re-entry, G-forces during descent, the impact of the landing, and then trying to stand under full Earth gravity. After years with bones and muscles adapted to 0.38 g, ISS astronauts need weeks or months of rehabilitation after 6 months in space. Imagine after 3 years on Mars. Studies predict that in conjunction-class missions, the most likely for Mars, lasting 1,000 to 1,200 days, 100% of astronauts would develop osteopenia, and 33% would be at risk of osteoporosis. And it's not just bone. Muscles atrophy. The cardiovascular system adapts to low gravity and loses the ability to pump blood efficiently. Returning to Earth could literally be fatal. So maybe Mars might really be one way only. Now let's talk about the history. Since 1960, about 56 missions have been launched to Mars. Overall success rate? Something between 40% and 50%, depending on how you define success. 1999, Mars Climate Orbiter disintegrates in the Martian atmosphere. The reason? A conversion error between metric and imperial units. Cost $193 million. 2003, Beagle 2 lands intact on Mars, but one solar panel does not open. No communication. Mission lost. 2016, the European lander Schiaparelli crashes and explodes on the surface. And these are robotic probes. No human life at stake. With humans on board, the margin of error is 0. There is no try again in 26 months. There is no software patch sent from Earth. If something goes critically wrong, you die on Mars. If this kind of raw truth about space exploration fascinates you, leave a like. Comment what you think. Is the risk worth it? And subscribe, because with each episode we delve deeper into the real challenges of conquering the cosmos. Before finishing the video, I left suggestions for topics for the next episode here in the comments. I would love to respond to you and make a video about your comment. In the end, I will leave a suggestion video. I will really enjoy your presence. Mars is not impossible, but it won't be easy, and it will definitely not be safe. The first people to set foot on the red planet will be some of the most courageous in human history, or the most aware of the risk. Maybe the first generation of Martians will actually stay there, not due to technological failure, but by choice, building something new in an old world. Because in the end, the question is not just, can we return from Mars? The question is, should we? I left some suggestions for topics for the next episode here in the comments. I would love to respond to you and make a video about your comment. Stay tuned for the next episodes. The answers will surprise you.